This is Lecture 3 in BBSP 710. Today we're going to discuss observational studies and why they're considered inferior to controlled experiments and how you can maximize the chance of obtaining useful information and accurate information from observational studies despite the shortcomings of observational studies. So as you'll recall from the previous lecture, an experiment refers to a type of scientific process or experiment where you actively intervene or manipulate the experimental condition. You assign half the people to get the drug, half the people to get placebo, something like that. An observational study is you merely observe an existing situation, that you collect data from a large group of people, including both smokers and non-smokers, and see if the smokers are more likely to have lung cancer. Experiments are more reliable, but you can use observational studies if an experiment would be too costly or unethical. You can't assign half of your study to smoke, for instance. The problems with observational studies is, number one, it's by definition in the vast majority of cases a non-random selection from the population. In very unusual situations, you might be able to sample the full population in your observational study, but usually you just have to sample whatever data you can find. There's no way to control for confounding variables. And there's simply no solution to these two problems that will work in all situations. You just have to handle it on a case-by-case basis. So an example of how observational studies can give misleading results, and kind of a repugnant example, but just illustrates how bad statistics can be abused, is in the 19th century there was a movement to quote-unquote scientifically prove that certain races were inferior to others. So a man named S.G. Morton collected hundreds of skulls and measured their cranial capacities in cubic inches, and in this particular sample that he collected, the mean capacity of skulls of Caucasians was 87 cubic inches, and among Native Americans it was 82 cubic inches. And there's a fundamental problem with the study right out of the get-go, which is that, as far as we can tell, there's no association between cranial capacity and intelligence. But aside from that, if we wanted to show the different racial differences in cranial capacity, there's some statistical problems with Morton's study. He didn't sample from the population of all Native American skulls. He just used a convenient sample of whatever skulls he could get his hands on. And it turns out a high percentage of the skulls were from small-boned Incas in Peru, and there were very few skulls from comparatively larger boned tribes. And in the 20th century, Stephen Jay Gould reanalyzed Morton's data and controlled for the fact that he oversampled from a population of Native Americans with smaller skulls. Once he corrected for that, then the difference that had been observed completely vanished. And so this study illustrates why you can have problems if you select your experimental units non-randomly. And another potential problem is if you don't control for confounding variables in observational studies. A famous example of this was when the ultrasound was first introduced. A lot of people were worried that it could potentially harm the fetus when it was performed, and so they did some observational studies and found that babies who had had ultrasounds tended to have lower birth weights than babies who hadn't had ultrasounds, and this led to a minor panic for a while, but hopefully you see immediately that this was an observational study, not a controlled experiment. And doctors were more likely to use ultrasound if there were problems with the pregnancy, so it wasn't surprising that these babies tended to have lower birth weights. Later on, a randomized study was performed using only healthy babies, where some received ultrasound and some did not, or perhaps they received a placebo ultrasound. When they did that, there was no difference at all on the birth weight. And like you say, in general, there's no way to completely solve these problems of non-random selection and uncontrolled confounding variables. There are some things that we can do to minimize the problem. As you'll recall, confounding is when you want to show that there is an association, causal or otherwise, between variable A and variable B, but there's a third variable, we can call it variable C, that influences both variables, and it may be that the entire association between A and B is explained by the fact that they're both associated with variable C. So a famous example of this was in the 1970s, the graduate school at UC Berkeley was accused of gender bias. In 1973, there were about 8,400 men, 4,300 women who applied to graduate school at Berkeley. 44% of men were accepted versus 35% of women. And when you look at this, that seems like substantial bias. The men were significantly more likely to be accepted, but it turns out there's a confounding variable here, and once you adjust for these confounding variables, as I'll show you here in a second, the bias more or less disappears. And the confounding variable is that graduate admissions are made at the department level, not at the university level. So, first of all, if there's gender bias going on, it's going on in every single department across the university. But the confounding variable is that some programs are more competitive than others. And if women are more likely to apply for the programs that are harder to get into, then this can become a confounding variable. So this table shows the data for the 6 largest graduate programs at UC Berkeley. When they released this data, they didn't allow the departments to be identified by name, but as you can see, if you look at it department by department, there doesn't seem to be any major difference in the admission rates between men and women within a department. If anything, in Department A, women seem to be more likely to be admitted than men. Well, what's going on here? How do you explain the fact that overall departments combined, men are significantly more likely to be admitted? Well, if you look at Department A, note that there were 800 men who applied to this department, but only 100 women. Men seem to apply to that department much larger numbers, and that department was comparatively easy to get into. Whereas if you look at, for example, Department C, D, and E, C and E especially, you have more women apply, and I guess the same story that for A and Department B, that almost everyone who applies for Department B is male, and it's a relatively easy department to get into. Like Department C and E, you have significantly more women applying than men, and the admission rates in these departments are much lower. So it appears the difficulty of getting into a certain department is a confounding variable, though once you adjust for that, if anything, women are more likely to be admitted to most departments than men. This still isn't conclusive proof that no gender bias exists. You can, in general, it's hard to prove a negative in science, and when you're trying to prove a negative using observational data, it's particularly dicey. But if such a bias exists, it's more subtle, that the university deliberately has less seats available in departments preferred by women, or that perhaps female applicants are more qualified and we would expect to have more women across the board, and by admitting an equal number, there's some sort of bias there. We can't know for sure, but in any case, there is a confounding variable here, and the fact that 10, the acceptance rate for men was 10% higher than the acceptance rate for women, that isn't conclusive evidence of gender bias. And to give another series of examples of how we might control for confounding variables, we'll look at a study on smoking and birth weight that sometimes you can adjust for confounding variables by performing follow-up studies or using various types of statistical adjustment. That say there was an observational study that showed that mothers who smoke tend to have babies with lower birth weight. Hopefully you're already seeing that we can't establish causation here because it's an observational study that wasn't randomized and we can't eliminate all the confounding variables. For instance, in this study, they found that smokers drank more alcohol and more coffee than non-smokers. It's possible the alcohol or the coffee is affecting birth weight rather than the tobacco. In fact, another strange result of this study is the women who smoked reported they began menstruating at younger ages than non-smoking women. The vast majority of cases, menarche occurred before the women began smoking, so we can't explain this by the smoking. Maybe there's some sort of socioeconomic thing going on here that, I don't know, I can't really explain it, but one way or another, it raises the possibility that maybe the reduced birth weight may be due to the smoker rather than the smoking. So there's a couple ways that we can try to establish causation despite the non-ideal study design here. So one possibility is statistical adjustment. There was a follow-up study that measured every single confounding variable they could think of: age, weight, height, blood type, upper arm circumference, religion, income, education, etc. And they applied some sophisticated statistical methods to try to adjust for all these potential confounding variables. The result was there was still an association between lower birth weight and smoking, increasing our confidence that it isn't a simple case of confounding. But this has certain shortcomings. First of all, you have to, number one, think of all these confounding variables. If you forget about the certain confounding variable, then adjusting for the ones that you do think of won't help you. Even if you do think of all of them, you have to measure all of them accurately, which is usually going to take time and money. And even if you've done all that, it can be difficult to be completely certain that these other variables aren't confounding the association even with the advanced statistical method. And that's actually an active research area in statistics. Another way that you can try to tackle the problem is that you can look at an alternative dependent variable or an alternative outcome, which, for instance, another follow-up study for this tobacco study measured various things related to the functioning of the placenta. They found that smokers had more abnormalities of the placenta and higher cotinine levels, which is derived from nicotine in the blood, suggesting, once again, indicating that the association between smoking and low birth weight is real, because you wouldn't expect to see both placental abnormalities and low birth weight in smokers just due to chance. This is helpful, but first of all, an alternative dependent variable has to exist, and even if they do, it can be costly and time consuming to measure. It's still not conclusive proof of causation that maybe there's another variable like alcohol use that causes both the placental abnormalities and the low birth weight, and is it necessarily clear that placental abnormalities are going to be associated with low birth weight? That would also have to be established. Another thing you can do, particularly when human subjects are involved, is to do some type of controlled observational study, where, as I said, for ethical reasons, you can't ask half of your study to smoke, but you can still do some matching, as I'll discuss here in a second, to try to control for confounding variables. In this particular study, there were 159 women who smoked during one pregnancy but quit before their next pregnancy, and these women were individually matched to 259 women who smoked for 2 consecutive pregnancies. They tried to match them according to the birth weight of the first child, the amount of smoking during a first pregnancy, and every other confounding variable they could think of. Even after doing all that, the result was that women who quit smoking tended to have babies with higher birth weight, once again suggesting that smoking is associated with lower birth weight. Again, this will take time, it will take money, and you may not have either of these things, and you can't be certain that you controlled for all the possible confounders, and it possibly introduces new confounders. Maybe women who quit smoking are also likely to have quit drinking and other harmful habits. So, whenever you're using observational data, it can be very difficult to be completely certain of causation. Oh, now an extended example of an observational study involving human subjects. This was this example is the INCAP study, which was performed in Guatemala in the 1960s. It was trying to understand what causes malnutrition and what can be done about it. So basically, what they wanted to do was do some type of observational study comparing those who eat a proper diet to those who don't. And this presents challenges both logistically and ethically. First thing that you need to do to perform this experiment is you need to choose an outcome variable. How do you quantify malnutrition? One possibility is that you can just measure the impact on physical growth. They found that Guatemalan children tend to be about 5 inches shorter and 11 pounds lighter than children in the US by age 7. The big advantage of measuring children's height is it is very easy to measure as opposed to more subtle measures of malnutrition. The drawback is there's a lot of confounding variables here. There may be racial differences in height. These height differences may be due to disease, hygiene, access to health care, etc. Oh, they tried to, first of all, see is this a valid measure of malnutrition? The big confounding variable that could cause the problem is our genetics slash race potentially causing the confounding variable. Some groups, like say the Dutch for instance, are famous for being taller than most other populations. Is it possible that Guatemalans are just shorter genetically? Well, upper-class Guatemalan children in cities are racially indistinguishable from rural children, but they were basically the same height and weight as North American children. So it looks like the height difference is not due to genetics. Looks like it is probably the result of malnutrition and possibly other health problems. So they ended up using height as their outcome of interest here. And the next thing they had to do was develop their statistical design. The, the simplest approach would be to do a pure observational study, just find out how much food children ate while they were growing up, compare the heights of children who got enough food to children who didn't get enough food, and see if there's a difference between the two groups. Well, there's several problems with this approach. Number one is the sad truth is that almost all children in rural Guatemala don't get enough food. Second problem is in order to do this, you would have to know which children got enough food when they were younger and which children didn't, and it's obviously not something that people keep track of. Oh, that can be very difficult to determine, and there's no way to control for confounding variables like access to health care, clean water, whatever the case may be. So they decided some level of experimental intervention was necessary. And the statistically ideal design would be you randomly sample a treatment group and a control group from the population of everyone in Guatemala. You hold their environments constant and give one group enough to eat, and you don't give the other group enough to eat, and then you compare the heights of the two groups. Well, hopefully you can see immediately there's several problems here. Step 1, sampling from all Guatemalan children, is essentially impossible. Step 2, holding environments constant and giving one group less food to eat, is not only impossible, it's highly unethical. So, even though that would be the perfect design statistically, in the real world you can't do it that way. So what they actually did is they found 4 villages that were as similar as possible. They had comparable population, culture, diet, poverty and literacy rates, and so forth, and they assigned 2 villages to be the treatment group and 2 villages to be the control group. That doesn't confounding variables, but it greatly reduced. The treatment villages received a drink that is high in calories and protein, and the control villages received a drink that was low in calories and didn't contain any protein. And so the idea was they would compare the treatment villages and the control villages. And they were hoping to conduct an experiment where the confounding variables were controlled, but ethically you can't just say that half the children aren't going to get enough to eat. So in both villages, the children got to drink as much as they wanted, and the consumption varied drastically between individuals, and controls drank far more than the treatment group. So it ended up being an observational study. So, what they did is the observational nature of the study introduced a bunch of confounding variables: the diet, the amount of drink that they had, hygiene, the heights of the parents, how much money the parents had, etc., etc. So, they tried to control for all the confounding variables they could think of using the appropriate statistical methods. And then they examined the relationship between supplement consumption and height. And the results were that in the control village, the amount of supplement they had no association with their height, but in the treatment village, the children grew about an extra 0.04 inches for every pound of supplementary protein that they consumed. So the conclusion was that the lower height of Guatemalan children is most likely due to lack of protein, but we still can't rule out the possibility of confounding, that maybe the health care was better in one village, or who knows what's going on. So hopefully I've beat it into your head by now that just because two variables are correlated with one another does not mean that the two variables cause one another. And there's always a possibility there's some confounding variable that you're overlooking. But if you just sit there and stomp your feet and say, there's always a possibility of confounding, we can never be certain that we're overlooking something, and then you would never be able to say anything about science, and you would never be able to tell people to stop smoking, that it might give them cancer, because you would always say, well, what if there's a confounding variable that we're overlooking? So, in order to make any sort of scientific inferences, we have to establish some criterion where we can say A does cause B. Well, you can almost never be 100% certain that A causes B. You can consider various criteria to increase your confidence that there's a causal association between two variables. Oh, in 1965, there was a lot of debate. No, this wasn't just the tobacco companies being in denial. This was actual scientists who still weren't 100% certain that smoking caused lung cancer. So an epidemiologist named Bradford Hill proposed a set of 9 criteria to decide if two variables are causally associated with one another. And these criteria became known as the Bradford Hill criteria. And you can still never be 100% certain of causality, but if you're ever trying to show that variable A causes variable B, and you you want to try to show that as rigorously as possible, you should refer to these criteria and see how many of these criteria you can check off the list. And so the criteria briefly are listed on the next two slides. First criteria is the strength of the association, that strongest correlations are more likely to be causative than weak ones. Smoking and lung cancers is an extremely strong correlation. As I recall, you're something like 15 times more likely to develop lung cancer if you smoke than if you don't. Whereas if you were only 1.2 times more likely, you'd be much less certain. Second criterion is consistency. Do you see the same correlation in a range of populations, areas, subgroups, different circumstances? The association between smoking and lung cancer has been found in every country, every culture where it's been studied. It's been found it's consistent among racial groups, consistent among socioeconomic groups. Any sort of possible subset, you see the same result, increasing our confidence. Another, the next criteria is specificity, that a predictor is correlated to a single outcome is more likely to be causal than one that's correlated to multiple outcomes. Famous example, something that's not specific, is socioeconomic status. If you're poor growing up, you're more likely to get a wide variety of diseases, but it probably isn't being poor that causes the disease, it's lack of access to health care or something like that. Smoking, on the other hand, it drastically increases your risk of lung cancer, but it doesn't increase your risk of that many other diseases. I mean, a few other things, but it is quite specific to lung cancer. Next one is temporality. Does the predictor happen before the response? If people started smoking after they got lung cancer, then that would be less convincing evidence of causation, but in almost all cases, people start smoking the long before the lung cancer develops. The next criteria is gradient, that when the predictor increases in either magnitude or duration, does the response increase? That's also true for smoking. Numerous studies have shown that the longer you smoke, the more likely you are to develop lung cancer, and the more packs per day you smoke, the more likely you are to develop lung cancer. Another question is, does the relationship make sense? That it does seem quite plausible that, that's a bit subjective, but it does seem quite plausible that if you're putting a bunch of junk and chemicals into your lungs, that might have negative consequences. Another criteria is coherence, is the correlation consistent with other known relationships. For example, chewing tobacco has been associated with cancer of the mouth and throat, once again suggesting that there's something carcinogenic in tobacco. And next criteria is experimental evidence that correlations observed in experiments are more likely to be causal than correlations observed in observational studies. Obviously, you can't do experiments involving smoking. Well, I mean, I should take that back. They actually have done experiments in mice and found that mice that are exposed to cigarette smoke are more likely to develop lung cancer. So, even though you can't do it in humans, if there's experimental evidence that's available, that increases your confidence. And the final criteria is analogy, or other types of relationships believed to be causal based on similar types of evidence. And, well, I'm trying to think of a good one for smoking. I mean, maybe something like BMI and heart disease would be the same sort of thing if you did a similar type of study involving BMI and heart disease. It would increase your confidence that you came to the same conclusions regarding smoking and lung cancer. So the things to remember for today's discussion is that observational studies are problematic due to non-random selection and uncontrolled confounding variables, and you have to try to control for confounding variables using a variety of different techniques, either statistical adjustment or doing some type of matched paired design or limited experimental manipulation. The best approach depends on the problem, and you can never conclusively prove causation, but you can provide strong evidence of causation using the Bradford Hill criteria. These days, no one seriously doubts that smoking causes lung cancer, despite the fact that a gold standard controlled experiment has never been conducted.